So this homework, one group did great in this homework. They had 4 people, and then members. Everyone else did okay.
If you right click on the tab, back up your top,
Yeah.
yeah, you can press, no, like at the actual tab.
Oh, here.
Yeah, you can press duplicate.
Oh, yeah, yeah. Okay, that's helpful. You told me that a while ago.
I've been trying to figure that out the other day. I was like, oh, yeah, that could help.
Yeah.
I thought about immediately that way.
Yeah. Yeah, because it's like a lot, and it's all.
Yeah.
Actually, I don't really need all these things, I don't think. It's just the one thing. Let me go through this. So this I wanted you to go through the 4 things. I guess everyone kind of did that. It's in the notes. I haven't gotten through the notes, so it's kind of hard to say, but he's trying to say like all the possible ways you could transport through a polymer, through a porous membrane, like the bulk diffusion, interfacial, and you can absorb to the surface. Subdiffusion means that these are these polypropylene where they have crystals, and the material has to diffuse around a pathway, so it doesn't do Brownian motion. It's got to do a more tortuous path through the thing. There's cartoons for all these things. Whether or not it's true is another story, but subdiffusive dynamics and then spatiotemporal coupling with multi-scale relaxation processes. So I think the spatiotemporal is kind of like the jump diffusion thing. In other words, you have, in that case, you have like pores where the material goes to, and then it jumps to another, and that originated with metallurgy, like in terms of metal diffusion, like in interstitial sites. So it has, the metal goes to an interstitial crystalline site, and then it can pop to the next one. So there's a, in that case, there's a time associated with the popping, and there's a distance, it's like the lattice size. And they ported that model to like polymers, and they said, if you have like a disordered polymer, then you have kind of pores, and the same thing happens, right? So it's like if you look at that B book, it's all about metallurgy, and they've basically taken that kind of stuff and brought over into polymers. Like they had a model there, it was already accepted. It was easier to sell it once it was already accepted. In other words, you had references for it that you could cite, so that helps. Then what is the saying? Fixed window scan. So basically that's, so one group didn't even, they started talking about figure 2, you know. It's like, I'm not sure what figure 2 is. Oh, figure 2 is this thing. So, like they answered question B with not figure 1. You know? Anyway, so there's 3 things here. These 2 are fixed window scans with the energy. You list the energy here somewhere. Oh, 2 micro electron volt. So it's elastic. Oops, something happened. He's already muted, right? There were a bunch of other people here, though, right? Where'd they go? The people is muted. Anyway, maybe I'm muted now. So anyway, the dashed line, so if you have the mean squared versus 1 over temperature, then that's Brownian, that's diffusion, right? Like the mean squared goes with the diffusion coefficient times time. Diffusion coefficient is KT over the Stokes drag coefficient. So this thing should go linear with time if it's Brownian with temperature, right? So then everyone got the x-axis messed up on this too. It says figure 1, right, in this question. Figure 1, explain figure 1. So everyone was saying like the x-axis was Q, but that would explain here because x-axis here is energy. So I don't know where they got the Q is down here, but it's Q squared. So anyway, there is no Q x-axis. Like 3 groups of Q for the x-axis on this, and it's temperature. So temperature is kind of energy. So you see, like an activated process, something happens at some temperature, right? And the temperature is 273. So that's like the freezing point of water. And you're talking about diffusion of water. It's like somehow you should put a picture in of like something happens at the point of water. And the same thing is true in these other plots. So 1 over 273 is like 3.3 or something. So there's the inverse temperature plots for like Arrhenius plots, 1 over T versus log versus 1 over T, Arrhenius slopes of energy. It's expect a straight line, and then the slope is going to be the energy. So that's Arrhenius behavior for the diffusion coefficient. That's what you expect, right? And then when you look at bulk water, it's not Arrhenius. It's Arrhenius for the first point, and then it's non-Arrhenius. So bulk water has a weird behavior as it's approaching the freezing point of water, which is 3 point something here. 1 over 273, I guess it's 3.6 or something. So that's where the crossover happens, is where water freezes. And basically, he says in the paper, so this is super cooled water on the right. It's 1 over T, so it's low temperature. So super cooled water, when it's in the membrane doing this jumping through the thing, it just acts normally like Arrhenius, like it ignores the super cooled feature. And then when, at least he's proposing that, even though the only one point he has in the super cooled regime following the bulk, but basically he's saying this line. And then he talks about that this one doesn't, that's why it crosses. And the water, the normal behaviors that get to super cool water and the diffusion, it's non-Arrhenius behavior because something happens in super cool water. I don't know what, something that makes it not follow this thermal dependence. I mean, he kind of explains it in the text. Anyway, so there is this crossover point. That's one of the questions, but again, that one doesn't have Q as x-axis either. So anyway, there is no Q in here. This Q squared for one of them is energy and is temperature. The temperature is like energy. So basically you're looking at some kind of transition. So you're coming in and looking at this fixed energy that the material can absorb, and then it happens at some temperature. So the thing's kind of released, and this is in the polymer, so there's a fixed, so it doesn't depend on size scale. These are different Qs, different size scale. So for as far as the aromatic rings and the polyamide, let's see, I got the polyamides here somewhere. Let's see, down. That's pretty slow. Huh? So that's the trifunctional chloride, and then there's a bifunctional hydroxide, right? That condenses with that, the MPD. So this thing can spin. So that's the motion he's looking at, is the spinning of that, because this guy's kind of tethered. He's got 3 things that can't spin. So basically, he's looking at the spinning motion of that and this kind of highly cross-linked polyamide, right? So that doesn't have any size dependence down to the size scale he's looking at. So the size scale he's looking at is 2 pi over 2. So it's like 3 angstrom, right? So 2 pi over is like 6.4 something, whatever. So it's like 5, 6 angstrom, or maybe 5 angstrom. It's the size scale he's looking at for the largest thing, and basically there's no size dependence to that relaxation of that energy and that temperature. So it's complicated, but basically, I guess it could kind of make sense. I mean, he explains it in the text too. So basically, I wanted you to read the text and figure out what he was talking about. One group did this excellent, better than I can. The others fumbled around, I think. That's okay, because you looked at the paper, and that's kind of the point of it. Anyway, so the other hydrated, you're looking at actually the motion of the water through the material, and that seems to be dependent the energy of that transition depends on size scale. So if you look at small sizes, it's happening at a lower temperature, so lower energy, and then at large sizes it's happening at a higher energy. So it's going through different kind of barriers in the material, I guess, maybe something like that. Goes with the size scale for whatever reason. Anyway, it's an observation that it goes with the size scale, and then you can explain it with whatever story you want. So that's kind of what's going on there. Describe a fixed window. And the fixed window scan is that he's got a fixed energy window. So he's gonna march through energies in this thing too. So basically, he just looks at one energy window, and then how the transitions happen for that. Anyway, so Q dependence, independence, and then how are LA and SA motions decoupled? Again, like he explains this in the text, so 2 and 3, he's written them out. So this is just for the polyamide, not with water, like the dry polyamide. And that's got it's got a small amplitude and large amplitude. And the small amplitude is fast and the large amplitude is slow. And you can distinguish the two because the backscatter measurement and the time flight measurement measure at two different energy levels, and they can pick out these two because one's fast and one's slow. So the fast one's higher energy and the slow one's lower energy. So the backscatter, which is lower energy, can pick out the large amplitude one. They're both in both, but basically one of them is in the backscatter more than the other. The other's in the time of flight more than the other. He explains that in here, like he says that down below here. So again, like one group got that solidly. He says it right there, complementary timescales. Then everyone else fumbled around that thing. So I don't know, it doesn't matter that much. Jump to fusion, everybody seemed to get that. So except that the point of this is that there's two numbers you get. So diffusion, usually there's just the tau, like the relaxation time. But here, jump diffusion is going to have two numbers. It's going to have a size scale and a tau, like a frequency and a tau to it. So it's a two-number model. Like there's an inherent size scale to it, a step size, like a Kuhn length or something to it almost. So in that sense, it's different than Brownian diffusion. Brownian diffusion, you assume that there's no size scale. It's just moving randomly around, or more or less. So even though the original is like pollen grains are jogging around, so they actually have like kind of a size scale. It's just a different way to look at diffusion, I guess, and it's fitting for these membranes. It's one model. Look at it. If you want to modify the structure and then affect the diffusion, then you want to use, this is a good model to use because it's structural based, right? And then curves for translation diffusion coefficient for bulk water and for water. That's the thing I said before. They cross because of the oh yeah, one group's also said like these show, so these curves, so that the sharp peak is the elastic peak, which is the first term in that equation 2. I didn't mention that. So the first term in wherever, not equation 2, the first term in this thing, this term, right, where you get the mean free path, that comes from the breadth of that first sharp peak. And then the green one is a remainder that's modeled with this Lorentzian function where you get a kind of a relaxation time out of that. So basically those two curves have two different components, the fast and the slow. So in other words, there's two kind of bell-shaped curves within the green, and you're fitting it with the two bell-shaped curves. So the time of flight is dominated by the low amplitude, I guess, and the backscatter is dominated by the high amplitude, but they both have both, and so you fit them with the two of these Lorentzian functions. That's kind of the one group talked about that and asked some questions about that too. So anyway, again, there was one like super group on this, but I think it's people that are working in this area. would explain that. Then I said, like, this has got to do with supercooled water, and he describes it right below. Like he talks about that kind of, or right around this plot somewhere, he talks about that. He talks about the crossover and excessive bulk like water, blah, 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 blah. All right, so that's about it for that. Any questions on that thing? I mean, everyone did okay. Everyone looked at the paper, which is what I wanted you to do. So that was good. It's a complicated paper. In fact, this field is pretty complicated. It's simple but complicated. It's simple in the sense that you're just doing some goofy process where you do a phase separation and then it results in some kind of structure and you find out that it's useful. Right, so it's all empirical from the start. It isn't, no one designed these membranes. They just did it and they found out like that could work. And then later on, people have applied like all these models to it, and the models are pretty complicated. So, and then there's other, and also like this week's homework, there's other solutions to the problem, right? So you can, so for, and this week is about gas separation membranes, which are like solid membranes. In other words, that the polyamide thing was porous, right? And then this is solid. So within the solid, you can do different things to get around the problems. So the paper this week, he talks about the limitations. Like in other words, if you have a solid polymer, there's an actual, you can calculate a limitation, the maximum separation you can get between two gases passing through a solid polymer. And there's no way to get beyond that barrier, theoretically. It's partly empirical, partly theoretical. They did measurements, they found out there's a barrier, and they have some equations that can predict that barrier. And you can go to different polymers to say how you could improve it, but there's some limit to improving that. So you can get around that by sticking things into the polymer, like transport, like ion exchange particles and things, or you can put liquid domains within the polymer that affect as a barrier. And then you can do things like burn the polymer. So then in the end, in the paper this week, he burns the polymer to make the graphitic. So he starts with one of these 100 micron or 50 micron films, and then he burns it. Then you can get layers of carbon. And then because the layers of carbon are oriented, ethane, which is a linear molecule, can pass through it, but ethylene, which is kind of bent more, can't fit through it. And then you can turn a film that had like a 5 selectivity for ethane over ethylene into like 20 by burning it. So it's kind of an odd thing to do, but basically there was some logic to it, and there's anyway, so it's kind of weird what you can do. You can also embed like inorganics into it. So there's a bunch of things you can do, like zeolites and things to make porous structure, nanopores in it. So I've already kind of talked about these things. So the paper, yeah, he mentions in the paper this week, like liquid filled pores. You can fill these pores with something like a ion exchange fluid, and you can actually like have like a reaction, like you're doing, trying to transport copper ions across it or some other kind of lithium ion, whatever. Then you can have a kind of a redox reaction going on in the pores, and then it can like one reaction on one side, another on the other, like acid base on the two sides, and you can get transport through these nanopores that are basically liquid filled up of the capillaries of a porous membrane, right? So there's a lot of different technologies involved here. Electrical separation is another one. So basically, that's like the hemodialysis membranes. There's going to be like a positive and negative field to pull off the salt from the urine or whatever, blood, I guess, but I guess blood, not urine. They generate something like urine. Anyway, so yeah, this week it's this gas separation. So the main thing is like the flux across it, right? So the flux, it's going to be the pressure difference drives it. And then the thinner the film, the better the flux, and the larger the area, the better the flux. And then this PA is the permeability. So the permeability is going to depend on solubility, which is thermodynamics. And then, so what it has to get into the film, so that's the solubility. That's a miscibility. And then it has to transport once it's in the film. So that's the diffusion coefficient. So you can't kind of measure those independently because you can only measure flux, and you know the thickness, you know the pressure, and you know the area. So you can just measure that one number, but that one number is made up of thermodynamics and transport coupled. Right. So then you have to kind of resolve those. That's the idea. So that's how much stuff gets through. Like if it's ethane and ethylene, and you want to push the ethane through and keep the ethylene, then you want to have a high flux QA for the ethane going through it. So then there's the other thing, like how much ethylene sneaks through, like how much of the bad stuff gets through. And that's going to be this selectivity, like the ratio of the permeability, which again has two numbers in it, of the A component and the B component. Right. So these two things, so usually you plot this flux or the permeability of the membrane, or you take the flux and divide it by, or multiply it by length and divide by the pressure and area, and then get like just the permeability, like a unitless, a number that doesn't depend on the parameters of the formation of the membrane, but just the material parameters. So anyway, so you can plot the permeability of your good stuff versus the selectivity, and that would kind of give you would want high of this and low, and high of this and high of that, I guess. So basically you do an XY plot and find the point. They find out that they're inverse to each other. Right? So the more selective it is, the less flux you get through. So it's not, you can't make a perfect one. So the only way you can make a perfect one is make them really thin. So get the good selectivity and then make it really thin. And then have a really high area and try to increase the pressure as much as you can. But the higher the pressure, the more you'll blow out the membrane. So you need thickness to support the membrane too. So it's kind of like a bunch of engineering problems with those two simple equations. It's like the flux. This just shows like the flux for rubbers is really high, but the selectivity for rubbers is really low. And then the flux for something like acrylonitrile is really low, but the selectivity is huge. Right, so you kind of lose out on anything that you pick here. So you have to use these engineering properties to try to solve that problem. That's the general idea of this. I've already gone through some of this stuff. I showed you this before about how you can coat to. So if you make it so thin, so your L is so thin, then you have defects, and you can coat it to prevent that with something that's got a high permeability, like you can coat it with something like PMS that's got a huge permeability, and that when the thickness goes up, like in the holes, the L gets big, then the flux gets smaller, so that redirects the flow to the separation part. As long as you have a big enough hole that fills up with a thing with a high flux. So the high flux, if you get a thickness thick enough, then there can be a balance between the high flux and the. It's basically you wouldn't use PDMS, you'd use something in this chart that would match it out. So if you doubled the thickness, then it would be the same transport as a separation layer, and then you wouldn't need to worry about the cracks in the thin layer. Right, so that's kind of the idea. There's a balancing act between how much you can get through total and then preventing transport through these holes, which has no selection at all. Right, so that's just showing the relationship between transport and solubility for different gases and different polyamides. So these polyamides are the nitrogen polymers, like that I showed. These polyamides of these things. So that's an imide ring. So it's a benzoimide ring, and this thing has polarity, so it's good with. This turns out to be a really strong polymer, so it's also good at separation because it's got a lot of free volume. Not sure, it's not on this list. Basically, it's got a lot of free volume, so you get passage of gases through it. So anyway, this is just looking at, for different kinds of polyamides, there's a relationship between transport and sorption. Right? So you can find optimum materials in that sense for within one category of and then this is showing how the transport of the gas changes with the size of the gas. So let's see, the drag coefficient increases as the gas gets larger. I think this is just a plot of 1 over the size, right? So I mean, this is basically a measured number, and these are two measured numbers plotted against each other, right? So it depends what you're trying to transport through it, small or large things. Then anyway, you can see there's a lot to this. This is relating the critical temperature to the solubility for different gases, like the critical temperatures of each of these gases versus solubility in different polymers. So polysulfone and silicone rubber, these are like, so polysulfone is this SOO thing. This guy, like, it's got an S double bond O, sulfone in it, right? And you usually put aromatics to make it stronger. So let's see. And then this is just showing, I showed you this already, like how you do, like you cast, this is a hand casting, and then if you want to do that industrially, do the same thing, put a fluid in, and there's a casting blade, and then it casts it onto a rotating drum, and this makes a solid film in that case. And there's air to evaporate the liquid from the film. That's that could be a variety of things, but like a NIPS process, like non-solvent, solvent, non-solvent phase separation for making membrane. And then this is the same process, just expanded out with a belt. And then a thermal induced phase separation for the films would be like in a hot press in a lab scale, and then in a industrial scale. I'm not sure how they do it. I don't have a picture of the industrial scale thermal. I think it's just a heat dump into a heat chamber. That's just showing like how you can make these micropores films with radiation. So you can just blast it with ionizing or ions basically and blow holes in the membranes. And this, we looked through this before, like drying out polypropylene, you get pores. If you put starch into polypropylene, then you can wash it out. If you disperse it, you can wash it out and make porous polypropylene. If you want, it can be act as a kind of a filtration barrier. So let's see. So for the porous membranes, and we already talked about this phase separation methods. There's this idea that you can, this is cellulose membranes, and then basically do a solvent, non-solvent. So you dump it into water and it phase separates. That's kind of the idea. That's shown in one of these processes here. Right? No, not yet. Not there. Anyway, it's shown somewhere here. Here. So you cast, let's see. So this thing, you have your Dr. blade, you coat it in, and then let's see, starting with a fabric. You soak the fabric in the polymer, then you put it into water to phase separate out. So the water induces phase separation. This is an organic, like NMP solvent, and then it's going to phase separate once it goes into the water. And then you squeegee it and you run it through a rinse and then take up, and that makes a film. It's basically, it's a solvent-induced phase separation going on. The polymerization, that's the paper last week, the polyamide rope trick thing, interfacial rope trick. So what else is in here? This is just showing all the possible ways to do this solvent-induced phase separation, right? Because Not sure how important this is, but basically there's a history of how to do this process. What else is in here? So we already talked about, this is showing, this is a series, there's like 3 of these ternary phase diagrams. This is kind of what, so you have a non-solvent water and then a solvent, which is NMP, or is it whatever's listed here. So acetone water, this is dioxane, acetone, methanol, and polysulfone and NMP, polysulfone and DMF, THF, and ethanol. So you can see there's like proprietary mixtures of things that are going to be used to get the structure that you want. And always it'll be dumped into water. So the solvent could be a mixture of solvents, and it could have some non-solvent in it. Like ethanol would be a non-solvent, but basically, so this could be a complex mixture. This is always water. And then there's some polymer, but it could be copolymers, and it could be a mixture of 2 polymers. Right. So this is like a simplified version of what's going on. So you start with some kind of casting composition, right? It's mostly solvent. It's going to be like 25% polymer. And then you're going to go through this. This would be like the ideal phase diagram, right? But as you go through this, then once you reach a phase diagram, you actually separate into 2 phases of different composition on this map. So it's a little bit more complicated than even this, but basically, as you dump it into water, you get the non-solvent, then you reach the binodal line. So how fast it goes from there to there depends on if you get binodal, which would be little domains, little spherical domains, or spinodal, which is going to be a network. And the network's probably better. So you probably want to have it rapidly get to like C inside the spinodal regime, which is in the middle. Inside the small regime that you have to pass through, you're going to get just isolated domains, which can't be leached out. So you can't really make a membrane out of that. You just have droplets. So you kind of want the C part, the spinodal part. So somehow you have to get to that fast. How fast you get to that depends on what you put in for the solvent, the temperature, the exact details of the process that you're going through. Anyway, so this is like kinetics. It's going to decide the structure. This point, you have the phase diagrams laid out by thermodynamics, but basically the kinetics is what's deciding here. And then it's going to separate into 2 things, like the non-solvent and solvent parts. Like there's tie lines across this phase diagram. So you're going to get like a composition here, a composition down here, right? So it's not really one line after you cross the phase separation point. It's 2 points. Then final membrane composition. This after this point, this is mystical. You know what's going on. I think it doesn't. So this is kind of showing a little bit of how it could be complicated. So you can map out. Bottom line is that these ternary diagrams are the main thing that people are doing for the NIPS, the non-solvent induced phase separation membranes. This is just some of the things you can make with it. Oh, these are the polyamide. This is a chemical reaction. No, wait. This is NIPS, I guess. So you can do NIPS with polyamides, or you can do the nylon rope trick with polyamides too. There's 2 ways you can use polyamides. I think this is NIPS though. This one. So it went through that kind of process. And this is TIPS, which is thermally induced. Basically you have a solution and then you're going to somehow maybe put it in cool it down to get it to phase separate. And you can also, there's more complicated, like you could have 2 solvents. The solvents phase separate, and then one of the solvents is miscible with the polymer and the other one isn't. So you can get, so there's many complications and different routes to go down in this thing. So this UCST, upper critical solution temperature, could be for the 2 solvents. And the polymer might be immiscible in one solvent, miscible in the other. You might be separating out the solvents and the polymer is just following along with the separation of the solvents. Or it could be the polymer solvent immiscibility diagram, and then you go into separate all this, basically a solid polymer, this percent solvent. So the polymer is over here. So you get a solid polymer film, basically with almost 95% polymer on that side of it. And again, like if you do this slowly, so the cooling is slow, you end up in binodal, that's useless. You cool quickly, you end up in spinodal, you get a web-shaped structure, which is what you want for separations. And so this kind of process is going to lead to micron scale. So it's not going to give nanoscale pores. This is going to be like a microfiltration, about similar to like the processes like when you're stretching out the polypropylene to get the holes in it. Those are a little bit larger. And the washing out starch or something from the film. Right? Those are pretty large. Those would be like 10, 50, 100 micron. Right? And this thing's maybe going to give you 2 micron, but it's not sub-micron, so it's not a nanopore, that process. But you can see like 50 microns. These are 10 micron pores that are formed in the same polypropylene. This is by cooling into a phase separated region for the polypropylene, whatever solvent they use. Water cooled chill rolls. That's like a shock treatment, like a T jump to get some kind of spinodal structure if you can get it. Cellulose acetate. This is an evaporation process though. So you can also change the concentration, and that can drive you into the phase separation behavior region, wherever that thing is. So so you can do a non-solvent to drive into the non-solvent. You can just evaporate it. So if you just drive it up towards the polymer region, then you can get into the 2-phase region. I mean, it'll separate out as you dry it out. So it's possible to get to these structures by like 3 different routes: evaporation, thermal, or quenching in the non-solvent. And all 3 methods are used, right, to get a porous membrane. And then this is a process where you start with a polymer and a solvent, then you put it into just a humidity chamber. So you don't dump it into a bucket of water. The water in that case diffuses through the surface. You get phase separation at the surface. So you can get a spinodal at the surface and some kind of coarser grain structure internal. Right, so this environmental chamber things you use because you can get a gradient. It's easier to get a gradient and kind of control it in the process. Right, so this is the kind of the recipe, right? So it's got some surfactant in it, plasticizer. You're starting out with cellulose nitrate, cellulose acetate, and then there's a solvent mixture and a non-solvent. So non-solvent is coming in through the humidity chamber. And there's some non-solvent in the feed stream. So the polymer will dissolve in this mixture, but it's got some non-solvent in it. And then you add more non-solvent that drives the structure to form. So you can see this was cooked up. Like this is cooked up. There's not really any science to it. It's just like trial and error. We already looked at this from the last paper, this kind of anion condensation thing, forming networks. So this is a method you can make a film. So really thin film. So you see like 0.5 micron film. So, or you can make it thinner than that if you take that film and dry it out. So you can make this is how you get like a 50 nanometer film. So so Langmuir trough means you put something that's insoluble in water, like a surfactant, or something on the surface that forms a film on the surface of the water. And then if you have 2 Teflon bars, if you separate them, you can stretch that material across the surface. So that's called a Langmuir trough. Then you can make a film of like 0.5 micron, 500 nanometer film. And then you bring up from the bottom like a polysulfone porous substrate, and you just pick up the film with it. And then you have a bilayer if it sticks. Right. So that can be done like industrially. You can do that industrially. They're kind of showing this is the process to kind of do that. But basically, in a lab, you can do it, and you can also adapt it to industrial. You can see it's more complicated, and there's going to be a lot of problems with holes in this thing, because you're going to basically dry that 0.5 micron film out to get 0.2 micron or smaller, 50. So that's 20 nanometer films, right? So that's really thin films that you can make by by drying out the picked up film that you make that way. Let's see. This is just showing like the various problems you can run into. Like, so you have a support, and then you have a membrane. So ideal would be like that. Two is low pore densities. There's not enough holes in your support. Pore penetration. Your membrane material enters the pores. Incomplete coating. You have holes in the separation layer, and then the support isn't good enough, so that'll break when you try to use it. Right. So there's various kind of problems with membrane separation stuff. This is just showing you can, so this kind of, you think plasma is like in a lab and you have a bell jar and then you have electrodes and it makes this plasma, you can coat things with it, like with a SEM, you coat metals onto to make a conductive surface. But turns out you can do this in an industrial process. So they have actually like car paint coating machines that put plasma on, where you run steel through a thing continuously on a conveyor belt, and inside the thing there's a plasma where they coat, right? So this kind of plasma coating is already industrialized, even though it looks like something you do in a lab. But basically, you can make an extremely thin film that way, like maybe 10 angstrom, maybe less, right? So basically, this is the way you could make possibly the thinnest film that you could make, right? But you have to make a plasma of whatever, then you got to what they call plasma polymerize onto the surface, which means like you shotgun the monomers, basically blow them up, and then they make some kind of glue on the surface that can be really thin, right? So, anyway, so that's one way to make a polymer membrane. Then spin coatings, that's also done industrially, but something you'll see in the lab. You'd put a dilute solution in your polymer and spin it down. You can make something that's really thin, nanometer scale films if you want, right? Or you can make thicker than that. So we already talked about that kind of stuff. That thing we talked about, the idea that, I mean, pressure is driving the transport, and then you want to have thin fibers because pressure times area gives a force on the film, right? So if you have a 50 nanometer film on this thing, you don't want it to blow out. You want a small force on it. To get a small force, you have small fibers. Smaller the fiber, the higher the pressure you can do, right? So if you have a big fiber, big pressure, large area, huge force, right? So that's kind of the idea. You want to take it from a film, we have a huge area, and then high pressure just blows it out to like a capillary, as small as you can possibly make it. And then put a bunch of these into some kind of a device. So you make this tubular form with this kind of a dual injection. So you have a kind of air in the middle, and you have like well, you have air in the middle and you have the polymer solution going on the outside, then you do whatever you're going to do, like solution, temperature, evaporation to make the pores form, right? So there's easy process to make. It's just mimicking these other technologies, like this kind of casting technologies, but basically you can just do it with an extruder, right? You have some kind of a liquid extruder that's going to do it. And you can do that real time. So they call it a spinneret because it's making a fiber, and then you run it through. Say you're going to put it into water to coagulate it and wash it, heat treatment, whatever. Right. So you can either, if you want to feed in the middle air, or you can feed in the middle a non-solvent. You could feed in the middle water. Right. So then you could have different geometries for the pore structure. You can have a separation layer on the inside, a separation layer on the outside. Inside's better. So putting your water in the middle is the best thing, because then you can get your thick layer in the middle, and then the pressure is coming from the middle out. So then that's a better geometry than the pressure coming from the outside in. Right. So anyway, there's different ways you can make it depending on what you want to do. So there's that business. This is just showing more spinnerets and kind of the hierarchy of structure you can make for this thing. some pictures of different kinds of membranes you can make. This is kind of a picture of how you can make these stacked membranes. So basically, there's ways to industrially just stack these things up so that you get the fluid flow through a series of these membranes. This is kind of showing how to do that, but I don't think it's that important. These are containers to hold the fiber bundles for a membrane separation for reverse osmosis, which is typically how it's going to look. It's going to look like you have something like this, even though it doesn't look anything like the simple simple 2-layer model that you use into the thing. This just shows how to put those things together. It's a machine that does that. And then the different kinds of separation processes. I always showed you this thing. Somewhere in here is there some math. That's what I'm looking for. I've already looked at that. This is the electrodialysis where you have, so there's a charge across these. So you're separating each membrane separating like sodium and chloride in different directions because there's a charge difference across the middle. And if you stack these up, you can lead to channels that just have sodium and channels that just have chlorine, and then you can kind of precipitate out the effluent and then get pure water on the other side. So that's like a membrane dialysis. You put blood through it to kind of remove the salt and other things. But gas separation. So gas separation is always going to have two products. Like in other words, ethane and ethylene. So you have ethane coming out the bottom and ethylene over here. And then if your separation is 20 or 10 or 20, then you might need to run this through another membrane to like run the ethane through another membrane and then just keep continuing that until you get to the percentage that you want, the purity that you want, just run it through different membranes. Right. So, but there's always two product streams from a gas separation process. This is showing this idea that you can fill the pores. So in this case, they're putting hemoglobin into the pore, right? And then you can put oxygen in, the hemoglobin binds to the oxygen. So if it's oxygen rich, then the hemoglobin binds. If it's oxygen poor, the oxygen debinds from hemoglobin. So if you have a membrane and you have rich oxygen and poor oxygen, you can transport across it selectively oxygen if you have hemoglobin in here, like CO2 won't go across, carbon monoxide or whatever goes in with the oxygen. Right, so you just fill the pores with a liquid that's got like water with the hemoglobin in it, and then that'll just separate the. So that's like a carrier facilitated transport membrane. Right, and then this is like the nicotine patch that has a membrane in it that's used to control the transport of a organic across it, you know, with time control release. So anyway, then you get to this business. If you have a porous membrane, so there's a rule called Darcy's law, which is for sand, basically. So sand transport says that the higher the viscosity of the thing you put through, the lower the transport. And then the longer the distance, the lower the transport, and the higher the area, the higher the transport, and there's some constant. And the higher the pressure drop across the sand bed, the bigger the flux across it. So porous membranes follow this Darcy's law. And then solid polymer gas separation membranes are going to follow Fick's law, like Brownian diffusion. So you have a diffusion coefficient and the concentration gradient, which could also be a pressure gradient, right? So this pressure gradient and concentration gradient are kind of the same thing. And you have a constant out front. So these two laws kind of look like the same law in a sense, but one's depending on the viscosity of the fluid going through the sand bed, and the other's depending on this diffusion coefficient. It's like temperature dependent and got to do with like Stokes' law. Right. So the mechanisms for the prefactor is kind of a big difference between these two things. well, one's almost like macroscopic and one's microscopic, but the forms of the two are kind of similar. But this is how they look at it in the books. Like they look at it like the chemical potential on the two sides, the pressure on the two sides. So if you, for diffusion, the pressure is just a step, but the activity, in other words, the concentration drops. For Darcy's law, the concentration's constant, activity times concentration is like the activity, right? But basically that's the concentration. The concentration is constant across. You get a pressure change with the microporous, and the chemical potential drops. So it depends on if it's pressure or concentration driven. That's the point, which is basically the same as those two equations, right? And then this is looking at reverse osmosis versus osmosis. So osmosis, the pressure rises. If you have osmotic equilibrium, then there's a pressure difference. Like where the salt is, there's a higher pressure because the water wants to dilute the salt. So this is a salt side, that's a water side, right? And then chemical potential is equal on the two sides. And then the concentration is different on the two sides. So anyway, it's kind of interesting to look at these processes because they have different curves in terms of chemical potential, pressure, and concentration. We're looking at reverse osmosis and osmotic equilibrium. I mean, I'm not sure what, I mean, the value is like how you're going to write equations for this in terms of those things. Like with it, when the water goes to dilute, you get osmotic head. We talked about that before. So it's like a pressure, the water actually rises in the salt part to try to dilute it. It's trying to dilute the salt, so it drives across to reach equilibrium. And then this is a model of that jump diffusion thing. So again, it's got two parameters. One's a time parameter, like the tau, the relaxation time. One's a distance parameter, like how far it jumps every time. That people have modeled it, you know, across membranes versus particle size. Then I wanted to show you something else. This thing, I guess. This is one thing. It's two things. We have 2 minutes, so I can talk about it. Penetration. So if the particles go through, and then if they Brownian, so this is permeation, the rate of permeation for larger penetration. So larger particles get captured because the larger particles, let's see, how does this work? The larger particles get captured by the inertia, and the smaller particles get captured because they transport through the membrane like a gel permeation chromatography. So the small ones I think it's a label drawing. The small ones get separated by diffusion. They get trapped by diffusion, and the large ones get trapped by, yeah, I mean, the permeation drops. So the small ones get trapped by diffusion. Permeation goes to zero, and the large ones get trapped by hitting the walls of the sand, right? So it's kind of a point where you get most penetration for a particle size between those two things for a porous membrane, right? And the other thing is this. So you have Knudsen transport, which means like when things diffusion, it's got a mean free path, but it goes in a straight line before it turns, right? Just like a polymer has a Kuhn length. So basically, if you put a pore in that's smaller than that mean free path, three things happen. One is thermal transport goes to zero, because thermal transport involves collisions between the objects, like the atoms. If there's no collisions between them, you get no thermal transport. And at the same time, mass transport goes through the roof, because mass transport involves, because you've reduced the number of collisions between the atoms, there's no impediment to mass transport. In other words, the idea of viscosity is you have two particles and it has to squeeze through the two. Two of them never hit if the pore is smaller than the mean free path of the gas. So the transport shoots up like mad. So as you're going to pore size versus particle size versus gas atom size, at the low end, you see an increase in the transport for the smaller pores because of this Knudsen flow, because you confine the things and they're actually going in a straight line. They're shooting straight through the pores. And then when you get to the high end, so here it's just Purcell flow, like pipe flow. So the bigger the pipe, the more flow goes through it, right? So there's some kind of minimum in the permeability due to this Knudsen effect when you get to like nano-sized pores in the separation media. Right, so it's kind of interesting. It's interesting that the mass transport goes up, but the thermal transport goes to zero. Like if you can make Knudsen pores, if you can make an insulation material with pores that are smaller than 10 nanometers, it's basically like a vacuum. Right, so Knudsen transport. And the third thing is that interfacial transport takes over when the pores get so small. Those three things with Knudsen pores, which are pores smaller than the nutrient path of the thing transporting through. But anyway, so this kind of shows some of that, I guess, cartoon wise. I don't know what else is in here. Block copolymers we didn't talk about, but I think we mentioned. But anyway, you can imagine like you make cylindrical domains that you can use them for transport. That's the idea. You somehow break those out. But anyway, there's more slides, but that's about it, I think, for this. We'll go through another paper and try to. Actually, the papers are better because it makes you kind of look at one specific, a more or less specific area, you know.
Just like the random ones.
But just it's going to have like styrene butadiene. So you can have a run of styrene, and then you can have a run of butadiene, and they're a fixed length.
Yeah.
It's like tire rubbers, SBR, styrene butadiene rubber. The styrene separates out into glassy crosslink sites, and the butadiene's like rubbery. Yeah. So basically, if you can get the styrene monodispersed, you get monodispersed domains.
Okay.
So you can anionically polymerize to get these monodispersed chains, and you can make monodispersed pores. You know, and if you can make them into cylinders, then you basically have as if it was like an ion beam, but you can make this smaller than an ion beam. So ion beam is going to be like 50 micron, and this thing's going to be like 50 nanometers or 10 nanometers.
Yeah.
So you get a much smaller pore structure with this. You can also use like surfactants to make a zeolite. So you can take a surfactant and make nanoscale structure, and then put a sol gel ceramic precursor in. It'll template on the surfactant, then pull the surfactant off, burn it off, then you end up with a zeolite porous structure.
Yeah.
Right. Or you can just, like we'll talk about on Friday, you can just burn the polymer and make graphitic pores that are oriented. So those have a selectivity and shape too. The zeolites are basically round holes.
Yeah.
The graphitic are sheet holes. So if your molecule has arms on it, you know, it's not going to fit through the graphitic thing. But if it's a straight line, so you can select by shape that way. I mean, if you want.
Yeah.
And maybe with block copolymers, you could do that too, but it's hard to control it. I mean, they talk about electrical control and things to get the shape. Anyway, there's a lot to this, you know, it's like a huge area, actually. And it's all the polymer things, but it's kind of really applied. So,
Yeah.
anyway, so. All right, let's call it quits there.
Thank you.
Right.